Alright guys, I just looked up lithium iron phosphate powder. I gotta show you guys this. Look at this. Lithium iron phosphate powder for lithium battery cathode. That they meant battery. Cathode. 200 grams per bag. The bag's $44. You get 200 grams. With this, we can make a battery, homemade. The real question is, oh my gosh, we can make a battery! I'm freaking out right now. If I combine this with a couple other parts, we can do this. This is straight from China. This will be the cheapest price for sure of us to be able to do anything. And here's a picture of what it's going to come looking like. One of the guys that wrote this paper was Genki Kobayashi. Kobayashi is Japanese. Oh, these are all Japanese guys? No, not all of them. This sounds like Jean-Frédéric Martin sounds French. Yeah, as long as you don't get it wet. Yeah, so I can't sneeze. If I sneeze, it will start a fire. I want to know what the cost comparison is. 200 grams per bag. How many grams of cathode powder is in a cathode of a typical battery? See, the cathode is just a thin layer of powder on a long sheet, like this long. I feel like that thing could make a lot of those thin layers. Alright guys, so PVDF binder is what you look up on eBay, and you get it. It's for lithium ion batteries. You mix this with your powder to make it stick to itself and to whatever surface, whether it's a piece of paper, whatever you want. You mix this binder with the powder, and then you got to mix it with your carrier. And I still haven't learned about what the best carriers are, but I'm going to figure that out next. If you buy those three things, you mix them all together, you can create your ink or your paint. Okay, so we got our binder now. We found it. We've sourced it. Oh snap, so we're getting somewhere. Now, it might be that you can buy like elementary chemicals and make your own binder. And that would be something to explore next. But I think that for an initiate like me, I don't want to make it too complicated to start. I'll pay the extra money to get the binder pre-made. I'll pay the extra money to get the lithium iron phosphate pre-made powder. I'll buy all the powders in their stable pre-made form done in a lab by mass manufacturers. And I'm just going to mix them together because they're totally safe in their current form. Mix them because they're designed to be mixed. I've already researched which powders go with what. You get your binder, your carrier, blah, blah, blah. You mix them together. And you got your ink now, and you brush it on or you print it on or whatever. I'm not sure how they're going to do it, but I think you can even print it. I'm not sure. And I'll make the machine that will print it or whatever. And you buy the sheets that you're going to print it on, and then you got your conductive sheet with the cathode printed on, and then you got your sheet with the anode printed on. This side of the sheet is non-conductive, and so they're going to clap together, but in between will be the sheet that has the electrolyte. You push them all together, boom, that's a battery. That's straight up, literally a battery. And then you roll that up to make your jelly roll, they call it. And then you put that in a steel cylinder, and then you connect it to the bottom and top of the cylinder, and that's your contact points. And that's a 18650 battery you can make. And I believe you can buy 18650 battery, the steel shell, or make your own, or you can just leave it in the sheet form and just stack those and make battery packs like the LiPo battery packs are, and you'll just seal it off, crimp it or ultrasonically seal the ends, and then just have some wires coming out of that, which then are your code to a Dean's plug, and you plug it into that. So we can do this, guys. We can make batteries homemade, and I'm beginning to think it's way cheaper than buying them. Actually, way cheaper than buying them. You buy all the powders in bulk. These powders go on so thin, you're barely using any weight. So when you buy half a pound of powder for $50, it seems like, oh man, that's a lot, I can't do this. But then when you see that you're putting it on microscopically thin, one battery cell ends up being 1/50th of an ounce. Like that half a pound of powder will make you 300 batteries. And at $10 a battery you would have been spending, maybe $3 for some of these later battery prices have come down in the past 2 years, believe it or not. When I bought my lithium iron phosphate batteries in 2016, late 2016, I spent $10 each. And I got them sitting right next to me. That's a fact. I just looked it up. Now I found out you can buy pretty much the same thing for $3.60 each. The price has come down. It cut in half in 2 years. It's really incredible. But I'm telling you, for like 50, 100, maybe $200, you can make 300 batteries. That's my guesstimate. Let's say 300 batteries at $10 each. That's $3,000, but the price come down by half. So let's say $1,200. We spent $300 on powders to make $1,200 worth of batteries. That's a $900 savings. That's 75% off. That's a 75% margin. So if you make your own batteries and sell them, your cost of materials is only 25% the sale price, retail. 75 to 80% margins are pretty good for a commercial enterprise. Very good also for just saving money on your own, doing things yourself. And I can make these batteries gigantic. So normally you got a sheet about this big, and you roll it up and you make a little cylinder with it. Well, what if I made sheets this big, and I don't roll it up, and I just stack them? I can make some powerful batteries that are like, like this big, like huge. Like imagine a LiPo battery that's like 3 feet long by 2 feet wide by 6 inches thick, like just this enormous brick. You just lift it up, and it's got like enough batteries to power a car for miles and miles and miles and miles and miles and miles and miles. And it's not separate cells. It's just one giant brick. Is that bad? Wait, could that somehow be dangerous or worse? It seems like you'd save a lot of money on all the little steel cells. Why do you need each one in a little cell? Why not just make them as one big pack? Like one giant sandwich. That's almost like comparing, would you rather take 500 Twinkies for a wedding cake, each one's individually packaged, or would you rather just make a big wedding cake for everyone? Like, what's with the individual packaging? Why not just make one big cake? My thought is, from a mass manufacturing point of view, they figure we can sell these cells for all kinds of applications. Let's get good at making cells. If you want to put them in a car, we'll just put a bunch of cells in the car. But we want to get good at making cells because those can sell for all kinds of stuff. We want to make a cell that's small enough that it can fit in consumer devices and have multiple purposes, multifunctional. But if you want to save money as a DIY manufacturer of batteries and you have a use case where you want a giant battery, why would you make a million little cells? Just make a big battery of these little sheets of these conductive anode cathodes. I mean, it seems like a no-brainer to me. That'd be a lot less work, a lot less manufacturing, because you're not having to make each cell. You just have to paint the ink onto big sheets and stack the big sheets. Actually, these types of batteries don't use battery acid. Battery acid's only used for batteries that have like metal and then float in acid. I'm not doing that kind of battery. I'm doing the powder kind. It's powder mixed with a couple other things, something wet, and a binder. A binder is like a glue powder, and then you got your metal powder, metal compound powder, and then your glue powder, and then you mix it with your liquid thing, and then you mix it up into a paste or an ink, and then you brush it on the surface, and then that's your anode. And then you do that again for the cathode. You face them at each other, and then you put a powder and liquid together, mix it up, and you brush onto a porous surface. That's your membrane, and that is kind of like your acid layer that allows the ions to travel back and forth, and then you smash them all together, and those three form a battery. And it's actually the same as having metal, and then acid for the ions to travel between those two metals. But instead of that, you have metal compounds, because the metals are so reactive they burst in flames with air. So you have metal compounds that make it safer. And then you, instead of a floating acid layer, it's just a solid acid. It's a solid ion carrier layer, the separator, and you smash them all together, and it works the same way, but everything's dry. There's no floating, no liquid, nothing. It's all dried out at the end. The ink dries, everything dries. It's a dry process, and then you smash them all together, and those three sheets form a battery. PVDF is not too expensive. Right here, 80 grams of it is $50. And that's 0.2 of a pound. So a fifth of a pound is $50. And a fifth of a pound will make like 5,000 or 10,000 batteries. Because you only mix it as 1 to 2% of the total mixture of a tiny amount of powder spread out onto a battery. I mean, it is like a stupidly small amount then. Retardedly small. Like you're going to use 1/5,000th of a pound of this stuff per battery. That means 5,000 batteries can be made. So $50 for 5,000 batteries, that'd be $500. No, $50. $50 for 5,000. If it was $1, crap. If $50 gave you 50 batteries, that'd be $1 battery. If $50 gave you 500 batteries, that'd be 10 cents a battery. If $50 gave you 5,000 batteries, that'd be 1 penny per battery. So this comes out to 1 penny per battery. 1 penny per battery! And a battery's about $4. Sells retail about $4. So the cost for a $4 battery of PVDF is 1 penny. So that is not where your big cost is going to be. That is negligibly expensive, considering what it gives you then. Okay, how many batteries are you making? Great question. A Tesla car has 7,000 batteries in it, so I'm going to be needing to make approximately 7,000 batteries for the car. And then for my robot army, I'm probably going to need to make at least, maybe 10 to 15,000 batteries for that. And then for a big power wall, so I can eventually convert my house to solar, I'm going to need another maybe 15,000 batteries for that. So we're looking at about 40,000 batteries I'm going to be making. So I'll be buying a lot of this powder and a lot of all these materials over time. But like I said, it's going to be about 80 to 90% off the retail value of a battery by making it yourself. And that's huge. Instead of me spending approximately $60,000 for all those batteries, I'm going to be spending only 80% off of 60,000 is, well, let's see, 10% off, or 10%, no, we're spending 20% of that. 10% of 60,000 would be 6,000. 12,000. We'd only spend $12,000 to get basically 5 electric vehicles worth of batteries. And it would have cost 60,000. So that's a huge win. And it won't even be hard to make. You can mix all these things up in big batches of ink, and then just use a printer or a brush or whatever to brush it onto your sheets, and then dry it out, and then those sheets are good forever. And you can just like vacuum seal them into an aluminum package or whatever like they do, and then just store it. And those sheets will last forever. And then when you're ready, you just slap those sheets all together and you've got yourself a battery. So yeah, this is going to be something I'll be able to mass produce. I'll be able to have my own gigafactory in my room. So Elon Musk built a gigafactory for building batteries for his cars. Well, I'm going to build a gigafactory for building batteries for my cars and robots. And I'm building it in my bedroom. Elon Musk had to build a giant building for this in the desert, but I'm just doing it right in my office. So that makes me better than Elon Musk. Can you buy stock in my new business? Nope. Didn't you know I'm too greedy to share? How will you charge the batteries? Okay, I shouldn't laugh. With a battery charger? I mean, well, that was a cheeky answer. Okay, so with any battery, if you provide a higher voltage than what the battery is currently sitting at, it gets a charge. So you can charge a battery with another battery that has a higher voltage than it, and they'll level out one another. Or you can charge it with any power supply. There's a spider on my wall. With any power supply that has voltage output that is appropriate for charging that battery. You don't want to charge a battery at 1,000 volts if the battery only charges up to a maximum of 4 volts. You'd want to charge the battery then with like 4.2 volts. So you've got to have a fixed voltage power supply and limited amp power supply. You can't charge the battery with too high of amps either, so you use a MOSFET to switch on and off really fast the power supply in order to limit the amps that can flow through it, or the amount of joules of power per second, or whatever. So for that, you can just basically create a buck converter as a charger, or just buy a charger, but I'm saying how you'd build your own charger. But yeah, like a switched mode power supply can charge the battery as well. So there are many ways to charge it, but the basic idea is you just provide voltage at a safe amp level and the battery will charge up. Yeah, if you're charging thousands of batteries, the thousands of batteries are wired in parallel and in series. So let's say you have 5 batteries in series and each one's charge voltage would be 3, but since there's 5 in series it'd be 15 volts. So you need a 16 volt switch mode power supply, or a 16 volt battery, or a 16 volt charger to be able to charge them up. 16 volts would be higher than their collective volt at empty, which let's say is 15 volts. So 16 volts would be higher potential than batteries, so charge would enter them. And then you'd have your amp flow throttled as well, so you don't blow a breaker or whatever from the switch mode power supply that's gaining its electric from AC originally before it's rectified into DC and sent through a buck converter. So then if you're charging that row of batteries, the rest of the batteries in parallel will just naturally balance out with that row you're charging. Because when batteries are wired in parallel, whichever is the battery of higher potential will feed that potential through to the other batteries, charging those as well. So you can have 1,000,000 batteries, and if you just charge the first 5, if they're wired in series of 5, then the rest of the 1,000,000 would charge up based on those first row being charged, and all the other rows or columns would follow suit. As far as balancing the cells, no, you don't have to, because the way I set up my battery charging circuits, I charge each cell of a series individually. So even if some of the cells have lower possible voltage than the others because they're damaged and not balanced, they'll just get charged till they're full. The problem with the unbalanced set of cells is you just stick a charger on one end and the other end, and once one cell in the series gets filled and the others aren't full, then that one will get overfilled when the lowest one is still trying to fill. So for that reason, it's best just to charge them each individually. So I put little MOSFETs in between each one to decouple them during charging, and then I charge each one. But a normal balanced charging system basically has each battery, I guess, drain itself once it's at full charge and the others aren't. Through a resistor, it will just start emptying itself so that they'll all hit full charge together. But that's less efficient than my way, which is to charge each one at full speed, and once it's full, it's done, and it's shut off until they're all full. So you don't have to worry about trying to drain anything. Houston, we have takeoff. Check it out, boys. If you eBay NMP, you get N-methyl pyrrolidone, 1 quart, NMP solvent paint stripper, $34. That is your carrier. So it's paint stripper. NMP will mix with your lithium iron phosphate and your and your binder, which is your PVDF, to form your paste. This is the liquid aspect of your paste. You can't use water, but you need to have the powder converted to a liquid so you can paint it or brush it or print it or however onto your sheet of paper or plastic or whatever. And basically you're going to want 3 sheets: electrolytic sheet, cathode sheet, anode sheet. And you smash the sheets together and you roll them up, and that's your jelly roll. And then you put that in your cell. Or you just stack them up and that becomes your battery pack for the squishy pack like LiPo batteries have. And you need some kind of liquid as a carrier to mix with your powder to make a paste. You can't use water. This is the stuff you use. And it's inexpensive, and you don't need much. A 1 quart, $34 for a quart. I imagine you only need, this stuff dissolves out. It's not even part of the formula. It's going to evaporate. You only need, let's say, I don't know, 20 drops to make a little paste enough for a battery cell. Maybe 20, 30 drops. So, we're talking this quart would make thousands of batteries. For $33, $33 for 5,000 batteries. Again, we're talking 0.7 cents per battery, so very cheap. Less than 1 penny per battery is this material. So that's a win. So we're finding out these materials that go in might look expensive, but because it's such small quantities of it needed, it's actually dirt cheap. And I'm coming to the realization here that the materials are going to be very cheap to make a lot of batteries. So we're getting all the material sourced from eBay now. We're starting to run out of materials that we need to source still. We got our carrier, our binder, and our functional material. We've located them all on eBay now. Our carrier and our binder. Yeah. We got our carrier, our binder, and our functional material. We got it all. Okay. So that'd be it. I would make my batteries a certain thickness maximum. Maybe use LiPo batteries as the thickness. But I can make them long and tall. Normally LiPo batteries for hobby stuff comes like 6 inches by 3 inches. I think you should be able to make them longer and taller. Because that would save on... it'd be easier to build than these little compact packages. Make a big, long battery. And the thickness, maybe limit it to about the thickness of a LiPo, so 1 inch thick. And then just stack those side by side with a little gap between them. And then blow fans through that gap, and that'd carry the hotness right out of there. That's great. Thanks for telling me that. That will be useful. How can all these people in the comments be learning about this, and yet not a single person on YouTube has ever made a comprehensive video series of how to make your own lithium-ion batteries of any sort? There's nothing. At least I don't think so. Make your own battery pack. They're just using the cells. They're not making the battery. Then you got your shitty how it's made video where they don't show you anything except them extruding aluminum sheeting. And everyone in the comments is like, oh, If that's lithium, why isn't it blowing up? Which it would. Very, very false information filled video. A 4-minute video how to make a battery? I don't think so. I guess I'd be willing to listen to it. There's no way this will be comprehensive.
Meet Jane, who is close to earning a record score on her favorite smartphone game. Jane wishes her phone had a longer lasting battery, and Jane isn't alone. Anyone who drives an electric vehicle would also like their car to travel farther on a single charge. Lucky for us all, many scientists are developing better batteries right now.
Welcome to Advanced Battery Facility, a semi-automated battery manufacturing lab here at Pacific Northwest National Laboratory. Did your phone battery die? Here, let me show you how we're making batteries better so you can make longer calls, drive your car further, and store more renewable energy for the power grid.
Making a battery is a lot like cooking. The main ingredients in a battery are electrodes and an electrolyte. Electricity is generated when electrons flow through a wire that connects positive and negative electrodes. To control the electrons, charged particles shuffle from one electrode to another through a liquid electrolyte. The first step in making battery electrodes is mixing a batter-like slurry. PNNL scientists are exploring many different electrode materials, such as lithium, sulfur, sodium, and magnesium, that can make batteries more efficient. Next, the electrode glue is spread and baked onto a very, very, very long piece of metal foil. The flattened electrode is then cut into cell phone battery-sized pieces with a super-sharp stamping machine. Multiple electrode sheets are stacked together like a super... within cake, each layer separated by an insulating sheet and spit out of an automated stacking machine. Separated by an insulating sheet, stamping machine. Next, the electrode glue is spread and baked onto a very, very, very long piece of metal foil. The flattened electrode is then cut into cell phone battery-sized pieces with a super-sharp stamping machine. Multiple electrode sheets are stacked together like a super thin cake, each layer separated by an insulating sheet and spit out of an automated stacking machine. The stacked battery electrodes are then wrapped in a moisture-resistant barrier material. Finally, the second big battery ingredient, the stacked battery electrodes are then wrapped in a moisture-resistant barrier material. Finally, the second big battery ingredient, the liquid electrolyte, is injected into the battery. Next, the battery pouch is placed in a vacuum box, where all the remaining air is sucked out, allowing the electrolyte to soak into the electrodes. A few minutes later, the battery is finished.
But this isn't ready to power your phone yet. PNNL cooks up experimental batteries to test out new, promising materials. In addition to lithium-ion, our future phones and cars can be powered by sulfur, sodium, or even air.
To find out how well the new materials work, PNNL puts their experimental batteries through the ringer, repeatedly charging and discharging them in these test beds, where the batteries are exposed to extreme heat and cold.
This lithium-ion battery has been tested for more than 500 cycles, and it's still working great. Maybe one day you will achieve a top video game score, or drive your car across the country with a battery like this.
That video is pretty shitty as far as like helping you make it. But with my existing knowledge, which is becoming pretty comprehensive, I feel that was a little bit helpful. What fire? No, my car needs over 7,000 batteries. But each one's just a little cell that weighs 0.3 ounces. Or, I mean, 0.3 pounds. 3 ounces. Yeah, 3 ounces. So 5 of them is a pound. 50 of them is 10 pounds. 500 of them is 100 pounds. 5,000 of them, 1,000 pounds. 1,000 pounds of batteries. Holy crap. But it could be a lot less by taking away the cell and just making it lipo type. So maybe we can do like 700 pounds of batteries. which is like two of my father-in-laws riding in my car. One in the front seat, one in the back. Definitely makes my car ride lower. So I might have to somehow upgrade my suspension to handle the extra weight. Not to mention all the motors. Oh, that's all you need is stronger springs. Oh, I didn't know that. That's pretty cool. Yeah, that makes sense because your springs compress. And so if they're stronger, they'll compress less with more weight. Got it. So you can use your same shocks and struts, but just buy stronger springs for it. No, it's not going to skyrocket the gas because the batteries are going to do the driving. The gas is not going to be used at all. It's an electric car conversion. If I actually put 1,000 pounds of batteries in, that would be like 200 or 300 miles of driving before you run out. So most driving trips would be 100% battery, not even using gas, except for whatever gas to keep the engine in idle, to keep all the other systems running that require the engine to be at least on. But you won't accelerate using your gas pedal, you'll accelerate using your electric vehicle accelerator switch or throttle. Electric system throttle, separate from your gas pedal. Why am I excited, Mailbox? Because I fully understand how to make a lithium ion battery, and I'm going to save probably, I don't know, $50,000 and possibly start my own battery making company. And I'll be a battery factory.
For more amps, I would actually just keep this down like 2 or 2.5 volts and just.
Guys, I gave up trying to make a battery. I thought it's too complex and too expensive. That was wrong. So I'm no longer giving up. I'm going to make my own batteries for sure now. I overcame the complexity. I understand it now. It's actually not that complicated once you grasp all the little pieces you have to find from many videos, because nobody has a comprehensive video series taking you from step one, which I will be making. I put all the pieces together now. I get it. I'll probably make a lot of money on my lithium battery videos explaining all this. My batteries won't be half the price. They'll be 80% off the price of buying my own Tesla battery pack. 80% at least. Probably more.
Tesla Air.
Tesla Air. Oh, it's nice and clean in there.
Dude, look at how many torque checks there are.
The green stuff?
Yeah. But somebody's saying it hit the torque setting on my tool. I'm verifying.
So here's our first gen Tesla battery pack, right? We went from this to this. Slightly bigger. Anthony, how do you take up this thing apart?
Supposedly what these things are.
These bolts.
All right. So step one, remove all the screws. You need a 5/16 or 8 millimeter, and then T25. And that will do most of these screws right here. And then you got a couple of these little security torques. Probably gonna take the grinder to those.
Right.
You have a pair of vice grips. Some patience.
Yep.
And you can get those out. You have those little pucks, and you have to remove those.
Like a bolt, kind of bolt.
Oh, it's a reversible. Oh, I see.
It's actually functioning quite well.
Oh,
Aluminum.
oh, I see. So it's got a bolt with the inside. Yeah, it's just a wow. That's a pretty cool bolt. These are the alignment pins.
Yeah, I think so.
Yeah. Now at this point, you might be asking yourself, why is Spencer taking this perfectly good battery? You see, once a Model S is in a crash, it goes to a recycler, car dismantler, and you can buy the battery. And so then you take the individual components inside that battery pack, and then you can put them in cars like this. This is a Porsche 911. It has 10 Model S modules. So that's what's going to happen with the insides of that. It's going to be put into other projects. So So then after you take off all the screws,
You got the fun part.
you got the front tool. You got to pry it out
You don't want to just be presented by the actual cells, so you just want to kind of run the perimeter, slowly work your way around. These things are glued really tight.
until you can get a bigger tool to lift it, right?
Like four.
Yeah. Oh yeah. Oh yeah, those are cells right there already. Too close. Oh, there we go. Nice.
Oh, now we got drink coolant.
Oh, now it's starting to.
That's what we call it. That's the suit.
It's starting to.
I think our hit air bubbles. We roll that.
There's a fuse, 700 volts.
So, high voltage. Got a shrink tube, bracket, electrical tape on my socket, rubber gloves, rubber shoes, safety glasses. Some things we take very seriously.
Yeah.
Almost 400 volts DC. Not to be messed with.
In a moment of truth, the module is released from its prison. EMS crap out. Oh, look at that. You need to pull the whole module from these guys.
Right, you gotta, without bending it either. It's a very like fragile area.
Yeah. Nice.
I don't know if that's how that's done.
Well, there's no one is doing this. We're the only ones doing this. This is how it's done.
This is how it's done.
And so that's when you take a Model S battery apart. Now losing my place.
Show what EVs could really do, and to build and hardware an EV brand, large battery packs with the output huge power when needed. Large battery packs, however, are super expensive. Therefore, it is also desirable to offer smaller battery packs which are made far more accessible to most customers. To make a battery pack scalable to multiple capacities, it is necessary to have small capacity cells for a large number are connected in parallel. Let's consider the end of the i3 program. i3 uses very large 94 amp hour Samsung cells, all of which are connected in series to form a battery pack of 33 kilowatt hours. To offer a battery pack of, for example, 45 kilowatt hours, you cannot simply add cells in series. The voltage will change, and the BMS, motor, and inverter doesn't need to be modified. If we added a parallel string of cells of 100 cells, increasing the capacity early EVs, PHEVs, and hybrids used lithium iron phosphate cathode. Due to the high level of safety, relatively low cost, high power output, and good cycle life, however, they possess poor energy storage capability in comparison to their competition, and have a lower voltage. Most manufacturers currently use it. Lithium nickel manganese cobalt oxide catalyst, or NMC factory, therefore is typically only regarded safe for small cells, which are under approximately 6 amp hours. Consequently, for cells larger than this, such as those used in Lithium, Chevrolet Bolt, Renault Zoe, and BMW i3, NMC must be used rather than NCA. Let's move on to the other side of the equation, the anode. The anode of almost all lithium-ion batteries is a form of graphite. A strong desire is to transition to silicon, as silicon has the potential for significantly greater energy storage than carbon or graphite. For a given, as silicon has the potential, the anode of almost all lithium-ion batteries is a form of graphite. A strong desire is to transition to silicon, as silicon has the potential for significantly greater energy storage than carbon or graphite. For a given mass, silicon can store or charge. Proposal? Small volumes can change a little more than 10%. Silicon, on the other hand, undergoes a volume change of almost 400%, which in turn not only pulverizes the structure of the electrode on each cycle, but requires a great deal of space to be left for the cell to expand into. Typically, this is solved by blending a small amount of silicon oxide with graphite to form a composite electrode. The first generation Model S contains cells which have traditional graphite anode. The second generation Model S increased battery capacity, partially through the addition of a small amount of silicon to the anode. The 21700 cell in the Model 3 is almost certain to have a little more silicon blended into the anode than the current 1860 cell. Future cells will feature much higher levels of silicon. This is a major area of research and development for almost all cell manufacturers. So why would a combination of an NCA cathode and a graphite silicon anode like the Tesla? Well, it offers state-of-the-art energy density, which remains class leading today. Tesla's use of low capacity cells enables the use of NCA as a cathode material, which is attractive because of its great energy capacity. The addition of silicon to the anode will generally reduce the fast charge capability of the cell. However, as these cells are integrated into very large battery packs, each cell does not necessarily need to accept a large amount of power in order for the vehicle to accept a maximum of 120 kilowatts from the supercharging network. If you'd like a more in-depth video about battery chemistry,
other than they are significantly larger than the model designed with a more S and Model X, the 21700 cell to transfer the whole rank, they have a refined thermal management system, and they join both the positive and negative terminals to the same end of the cell rather than on the opposing end. The remainder of this video will focus on the modules used in Model S and Model X, as they are the most well known. So let's take a look at the first part. The condition of tech and properties of the module, demonstrating that located in 4 segments in top view and 3 segments in bottom view. As this is a module for 100 kilowatt cell pack, each bus bar segment will have 10 to 6 analog digital cells
a simple copper foil, very, very thin, about a meter long. And the second one of these is lithium. It doesn't look like lithium, but it's inside this coating where there's a very thin amount of lithium. And one other thing is that this is covered in electrolytes, which basically stores the energy in the lithium-ion battery. And then we have a simple plastic wrap that goes in between these two pieces for that. Because if they
Oh, this video is full of bad information. That white sheet is semi-permeable membrane that allows the ions to travel between cathode and anode. The copper sheet is the anode, the darker sheet is the cathode. The cathode is positive, the anode is negative. The anode, the copper sheet, has a graphite layer on it, which must have come off of this one. This white stuff is a semi-permeable membrane. It will have the electrolyte solution applied to it. The darker sheet is actually going to be an outer layer of plastic, and then a layer of aluminum, and then a layer of graphene, or graphite, and then a layer of cathode paste, which is your lithium metal compound mixed with a binder, which is a type of plastic powder, and then mixed with what's the name of that? Hold on. A carrier. The carrier would be NMP, which is like a paint thinner. And that creates your paste for your lithium metal oxide compound.
touch, well, obviously the battery is going to short circuit. And one thing I want to note about this piece is that this is basically where all your power is. This is the positive. Your copper here acts on the ground, so there isn't much power here. But this is where the potential of lithium-ion batteries and also the danger. Now, this can actually catch on fire quite easily, and I'll show you that in a few seconds. But one thing that has been done is people are adding fire retardant in between these layers. And the one problem with that is that will mean that your battery size needs to increase. And that's a big problem because you don't want to have a heavier battery. You want to have as thin of a battery as possible. And your jelly roll, which essentially when you roll all these together and fit it inside your battery, you want it to be incredibly thin. So the main advancements in battery technology are coming in between these two areas. First, how can we get this copper foil to be thin? And second, how can we get this lithium foil to be thin while still retaining a good amount of energy?
When lithium is burned, it is staked. Bright red color is produced. Higher temperatures produce plasma effect, which we can see in the center of the flame. Anyhow, I hope you enjoyed the video. Be sure to like and subscribe.
Lithium buttery. That's how you know it's Chinese people. Why am I making batteries? So I can get 80% off on something otherwise unaffordable? Lead batteries are too heavy. You would need to have lead batteries filling your entire passenger seat and floor pan, your entire back seat, and your entire trunk, just to come even close to getting the performance you'd need for an electric car. You would have no space for anybody to sit. You'd have to even stack lead batteries, lead acid batteries on the roof of your vehicle, and probably pull a trailer full of them as well, which is ridiculous. It probably still wouldn't be that much cheaper buying lead batteries than making your own lithium batteries. Probably be about the same price. But if you were to make your own lead batteries, that would be a lot cheaper, but like I said, it would be impractical, because they take up too much space for the amount of power they hold. Yeah, probably 2050 release date. Once I know exactly how to make a battery, my interest in making one will be completely gone. And I'm 95% there. I just want to make sure I have every last loose end tied and added into my notes, so that my notes form a step-by-step guide that show exactly what to buy and exactly how to mix it and exactly how to apply it and exactly how to construct the battery fully. I won't need to start making them until I'm well into my electric car project, or maybe well into robot building stuff. I mean, it might not be 2050, but yeah, it will be fairly buried on my to-do list for sure. I would say my research is complete. I filled in the final gaps in my knowledge with that careful note taking on the proper ratios of binders to what the conductive additive is and how much the ratio should be, and then what the proper amount of the carrier, proper ratio of binder to carrier to conductive additive to the metal compound itself. All those have proper ratios for how to mix them by weight. You use a jeweler's scale to measure the weights of everything to get it right. And then you mix it all with a mortar and pestle, and then you brush it on with an artist paintbrush or through a roller system that smashes it to a specific thickness onto your metal sheeting. And I established fully the types of metal sheeting, and that you need to put the inks on the top and bottoms of the two types with two separators involved, unless if you're doing the soft pack style, in which case the sandwich can be a little different configuration. And I wrote down the different configurations for each style, whether it's 18650 or soft pack. We'll be able to make both. And I think we will make both, just to demonstrate for our YouTube video series covering these topics. I'll show exactly how it's done, and I can show exactly where you buy these parts. I believe most of the materials you can actually buy on eBay. But some of the more specialized stuff, you'll have to buy through a battery materials provider website. And I found two websites, and I'm sure there's a lot more. I just stumbled across two very easily. That actually sell all the materials required. And I took notes on all the safety aspects built into 18650 cylinders that you put your jelly roll into. And so that was useful information to know how safe they make things. If I were to make my own DIY cell, it probably wouldn't have all those safety features. Yeah, man, I took notes on all kinds of stuff. Really filled in all the missing knowledge gaps that I still had. I can't believe how much missing knowledge I had. And now, it's truly thorough battery making notes. But because it was kind of sporadic and the information was coming all out of order, and I was finding little pieces here and there, and it wasn't really comprehensive in order, a full source with all this, I'm going to have to thoroughly organize my notes from a top-down level. And I think these notes will be so valuable to people that after they're fully organized, I might actually publish these notes in addition to my battery making video series. I think that having just comprehensive notes from start to finish on lithium ion battery making would be very much appreciated for somebody to read in like HTML format on my Art by Robot website. And that could bring a lot of traffic to my Art by Robot website, which would be kind of cool. Especially if I put ads on the website. It's already getting some traffic, maybe 200 visits a month or whatever. If I put ads on it, that's money in my pocket. So yeah, that was just so much information. These notes need to be reorganized now. But I'm glad I got through it. Every question I had is answered. I know exactly how to make a battery. And I could do it in my sleep. And it's so easy a baby can do it. The fact that people buy battery cells rather than make their own just makes them a laughingstock in my eyes. What kind of an idiot would do that when they can just make their own battery cell? I'll be the first person on YouTube to ever make a battery cell by himself. Shows how pathetic the average YouTuber is. That's why I'm everyone's superior on YouTube.